Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm going to talk about the flow of G1s through a circuit, and the question is how many? And it probably would be great if I could give a specific answer, but we're going to look into it and see what we can find out anyway. So let's look back at a simple circuit again that I started with a while back. We have a battery, a 9-volt battery, an 8-ohm resistor, and a 1-ohm resistor. And as you go around the circuit, the 9-volt battery, there's an increase of 9 volts through the battery, and then there's a loss of 8 volts through the 8-ohm resistor, and a loss of 1 volt through the 1-ohm resistor. And according to Kirchhoff's laws, the sum of the voltages around the circuit is supposed to be 0, and that's what the numbers show. Using Kirchhoff's law is one of the standard equations used in analyzing circuits. The current through this circuit is equal to the voltage source divided by the sum of the two resistors in this case, which means it's 9 volts divided by 8 plus 1, which was 9 volts, says we've got 1 amp of current. Nice, clean, simple answers, straightforward, and when you build it this way, you'll get numbers like this. So this is what you expect to have, and let's see what the particle model says when we start showing G1s flowing through the circuit. Okay, in general, this is what I've done in the past for the purpose of doing an analysis. The G1 has an assigned value of 1/10 of a volt. This is an arbitrary assignment made by me. There is no physical property that makes this real. I'm just assigning it that way. Ultimately, there'll be a value, but this one is just an arbitrary one made by me. In general, batteries add G1s and set up a voltage gain, depending on the number of G1s. Resistors lose and have a voltage loss. And the sum of the gains and losses of G1s around the circuit must be 0, which, as I mentioned, is Kirchhoff's law. Okay, and G1 interacts with objects, and when it enters a resistor, it will pass straight through, hit an atom, and scatter or be trapped as an orbital. It's saying this over and over. Being scattered or trapped means there are fewer leaving the resistor than entered. This is the cause of the loss of G1s, and it has a direct relation to the voltage loss because I have assigned 1/10 of a volt to each one. If you lose 10, you're going to have a 1 volt drop. But to calculate the number lost requires that we know what I call an interaction factor. This is a statistical number, and this is how I define interaction factor. It is the percent of G1s that are scattered or trapped, and it's proportional to the value of the sign parameter of the object. In the case of gravity, the percent loss, for example, through the Earth is proportional to the mass of the Earth. In circuits, the percent reduction is proportional to the resistance of the resistor. And the interaction factor, I sub f, is a virtual constant that makes these statements into equation. We generally call it a constant of proportionality. These are proportional systems. To make this an equation, you have to add a constant of proportionality. Only problem is I'm not really big on constants. You remember my video on dark matter in G? G, they say, is an absolute constant. In the particle model, it's not. And so I call it a virtual, give it another name, call it something, because I treat it like a constant, but it may have a different value under different circumstances, and you don't always know what those circumstances are. So that changes the circuit statement from a percent reduction is being equal to I sub f times the resistance R. Now, there is a way to calculate these values. I spent about 6 months working on the value of I sub f for gravity. The answer I got is almost unbelievable. And it's all preliminary, so I haven't quoted it, haven't told anybody what that value is. I haven't done the same calculation for circuits, so I don't know the I sub f value of the circuit for circuits, but I can show you how to get an idea of what the value might be. So as a start, well, let's just take a look at some values between, well, the value must be between 0 and 1. That usually a factor like this, in this case, is between a value of 0 and 1. So let's set I sub f equal to 0, and we have a 9-volt battery, and if it's putting out 9 volts, it has to be inserting 90 G1 particles into the stream, so 90 are coming into the 8 ohm resistor. Well, if I sub f is 0, the percent lost is going to be 0. You multiply the percent, you take 90 times the interaction factor of 0 times the 8 ohm resistor to get the loss, to get the number lost here, and then you can subtract that. Well, it's going to be 0. Well, that's not right. I gotta lose 80. I gotta lose 80 G1s. 0 doesn't work. Try 1. Same thing. 90 being inserted added by the battery. 90 comes in. Okay, so the number lost here in this case is 90 times the interaction factor times 8 is 720. So it's going to lose 720, and the number coming out is minus 630. That can't happen. That's impossible. You can't lose 720, end up with a minus number coming out. There's no physical way for this to be true. So 1 doesn't work. By the way, here's a problem with negative numbers. This is a perfect example of the problems you have. Now, David, my son, did a talk on Peter Erickson's book on negative numbers, and he explains a lot about why the mathematics sometimes causes problems. If you're doing the math and you think this is the right way to calculate it, and you do a calculation and it comes up with a negative number where physically a negative isn't possible, and yet you continue the math, you've made a big mistake. And how many times could this have happened in the past where the math looks right, but the physics is wrong? Okay, so I set it to something different. Let's take point 1. And you've got the 90 coming into the 8 ohm resistor. When you calculate the number lost, you get 90 times 0.1 times 8 is 72. Okay, I lose 72 and I have 18 left. All right, that works. I don't get a negative number. But when I put 18 into a 1 ohm resistor, 18 times 0.1 times the 1 ohm, I'm only losing 1.8 G1s. I need to lose 80 here, and I need to lose 10 here, and I'm not there. 0.1 isn't small enough. I need a smaller number or something else to happen to make this circuit work. Well, I could keep on trying, giving you example after example, just putting them up there, but I just said, okay, given what I know about this anyway, I'm going to set I sub f equal to 0.001. So what I'm going to do is I'm going to set point A. By the way, if I go back, you'll notice I have this point. The input to the battery is A, the output is B. Input to the 8 ohm is B, and then C. So there's 3 points I'm going to keep track of as to how many G1s are flowing through the circuit. So I set point A equal to 0 and calculate the value of point 8 after going around the circuit. And I did a spreadsheet. So here's I sub f equaling the number. Here's A as the starting point. Battery adds 90, get 90. And then I calculate using the formula how many are going to be lost, how many I have to lose, and it says that with 90 in, I'm only going to lose 0.7. Subtract 0.72 from 90, you get that. Then this is going into the resistor, and you find out you only lose 0.09. And you get 89.91 at back at point C, and so I throw that number into here, and I just go down and repeat it. This series has 12 different steps, 12 different cycles. You could actually think of this process as the fact that since the G1 particle is moving at speed c around the circuit, that in one very, very short period of time, I think I show later what that period of time is, that it goes around, gets this value, so it gets a new value. And you can see that the value at point A keeps increasing. I'm all the way up to 1,000, and yet I still don't have 80 loss. I only have 8.87 loss here and 1.1 loss here. So this is going to keep on going and going and going, each cycle getting bigger and bigger and bigger until I get to the number 1,000, or actually 999 at point A. Now I actually just looked at this and said, well, if I need 80, maybe if I make my numbers 10 times larger, I'll get there. And so I estimated that if I really wanted 80 at this point, I need 10,000 at this point, and I need 9,910 at point A. And so when you do that, you get 10,000 at B. So there's 10,000 entering the resistor, and you multiply 10,000 times 0.01 times 8, you get 80. Right on target. Of course, yeah, I picked the number. I picked 0.001, and I picked 9910, and yeah, I get precisely get 80. And it's going to take a number of cycles for the circuit to get there, but it'll get there. And then I've got, when I lose 80 here, I'm down to 9,920 at point C. And when you put that many into the 1 ohm resistor, you only lose 9.92. Well, wait a minute, I didn't get a 10 volt loss. I didn't get I didn't get 10 G1 loss, or I didn't get a 1 volt loss. I ended up with 0.9 volt loss. It's close. Is Ohm's law wrong? According to the TPM? Yeah, I'm saying Ohm's law is an approximation. Just like Newton's law is an approximation when you assume G is a constant, and that the force is dependent on R squared. That's an approximation. Ohm's law is an approximation. this might be more to the what's really happening. See, Ohm's law is close, but in my mind, it's only an approximation. And the problem here is you got to go through two resistors. Did that deliberately, just to show this point, that once the G1 particle goes through first resistor, there's fewer of them there, and that's something that Ohm's law doesn't assume. It assumes that somehow you might have the same number coming into both resistors, even though there's loss in the first one. So how many G1s do we have? This is now when the circuit reaches stability and your isof is 0.001, which is an assumption on my part, 90 G1s, I'm making an assumption there. But what it says is you're going to have 10,000 coming in here and 920 here. That's a lot of G1s. When you think of the current, when you think of the current flow here, the current through this 8 ohm resistor is the voltage lost, which is 8 volts divided by 8 ohms, which is 1. The current here is 1 amp. The current here is 1 amp, and yet I got 9,910 here, I got 10,000 here, and I got 9,920 here. The number of G1s is not constant, even though the current apparently is, we treat the current as if it were constant. And if 10,000 were able to come into this resistor, but it can't happen with this circuit. It can't happen if you're going to lose some. As you gain some here, lose here, and lose here, the numbers are different. So there's what I call a G1 base. The number of G1s gained or lost in the circuit is 90, plus 90 through the battery, minus 80, and minus 10. The question, why are the G1s flowing? Why are 10,000 approximately flowing through this circuit? Well, it has to do with the assumed values. I don't know why I picked the 1 with 1. This should have been 0.0. This is not the one I wanted to show, but nonetheless, it has to do with the fact that the interaction factor is 0.001. My apologies. Well, and here, this is where I'm talking about the cycle. If you assume the path around that circuit is like 25 centimeters, then it turns out that each cycle is about 833 picoseconds to get each one is that. And the circuit is building up the base. It's trying to find it. Let me change the scenario a little bit. Let's assume that the battery instantaneously, instead of having 0 in and only 90 out, let's say it has already, maybe it puts out 20,000 instead of 90. I mean, it adds 90, but at point B, you've got 20,000. You're going to find that this process is going to you're going to go through this process, but the numbers are going to reduce. These numbers go down until you get to the 10,000. Okay, so the battery along with the base is 9,920 or approximately 10,000. The battery along with the other components must accumulate enough G1s to make the circuit work. And that's responsibility of the battery and hence the responsibility in response to the resistors. My example is I use fake numbers, and these numbers are wrong. Don't take the numbers literally, but this does provide a clue about the process. When the particle model is used, when a mechanical model is used where the loss of G1s relate to the voltage drop and how the circuit finds the number of G1s needed to make that system work. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.